Hi, welcome back. We're up to Lecture 5, Segment 3. The topic of this lecture again is correlation. And in this last segment, I want to talk about some of the assumptions underlying a correlational analysis. We won't have time in this segment to cover all the assumptions in detail. We'll come back to them later in Lecture 6 and later at the end of the semester when we revisit a lot of the assumptions underlying some of these common statistical procedures. So, in this segment, we're going to talk about 6 assumptions. The first 3 are listed here. If we're looking at a Pearson product moment correlation, little r, that's used for situations where you have 2 variables that are both continuous. For now, we're assuming that we have a normal distribution in both x and in y. It's not necessary, of course, that you have normal distributions to find associations, but for now, in this intro stats course, it's easiest to start with that assumption. We're also going to start with this sort of simple assumption that the relationship is linear, and I'll show you that in a scatter plot. And the third one is this funny new word, homoskedasticity, which is best just illustrated in a scatter plot, and I'll show you that in a moment. There are other assumptions as well, and most intro stats courses or intro stats textbooks don't really emphasize these as much as I do. This is sort of, I emphasize these because this is an area of my research, is how to properly measure constructs in psychology. And measurement is a really important issue if you're assessing correlations. So you need to know that you have reliable measures, that you have valid measures, and that you have random and representative samples. So I'm not going to have time to talk about these 3 assumptions in this segment, but these are the main topics of the next lecture on measurement. So let's go back to the first 3. And number 1, that we have normal distributions for x and y. Well, how do we detect violations of that assumption? That's real easy. Just go back to our lecture on distributions and summary statistics. All you have to do is just plot histograms, eyeball them, see if they're relatively normal. If it's hard to detect, well, then you could run summary statistics and see how those look and see if they're normal enough to satisfy this assumption. So that was covered in the lecture on distributions and histograms and on summary statistics and in the first lab. The second assumption, for now, we're going to assume a linear relationship between x and y. Of course, there could be all sorts of relationships between x and y that are not linear, but for now, we'll assume linear relationships, and we'll see that in scatter plots. And finally, there's this assumption of homoskedasticity. And again, let me show you that in a scatter plot. First, to give you the definition, remember in a scatter plot, all the dots represent individual cases or individual subjects. The vertical distance between a dot and the regression line or the prediction line is the prediction error for that individual, also known as the residual. The idea of homoskedasticity is that those residuals are not related to x. Because if there were, then we might have some sort of confound in our study, right? The residuals, the errors, the prediction errors, should just be chance errors. They shouldn't be systematic. So if they're systematic, then the residuals will be related to x. And I'll show you examples of that in a moment. So the best way to look at this, as I've said, is to look at scatter plots. But again, what you want to look at is the vertical distance between each dot and the regression line. The best, most classic illustration of these assumptions underlying correlation and regression analysis, for that matter, were developed by a statistician known by the name of Dr. Frank Anscombe in 1973. And these are so classic and so well known that they've become known as Anscombe's quartet. And let me show you what they look like. What Anscombe did, which is extremely clever, just so elegant, and shows how it's so critical to look at your scatter plots before you run correlation analyses so you know what you're getting. What Anscombe did is in all 4 of these data sets, he made it so that the correlation was exactly the same. The correlation in all 4 of these data sets is 0.82. So a really strong relationship between X and Y. In fact, the variance in X and the variance in Y across all 4 data sets are exactly the same as well. It's very clever. But look at the pictures. Clearly, there are different things going on in each of these 4 cases. So this first one in the upper left is a scatter plot and a correlation that satisfies our assumptions for now. We have a normal distribution in X, normal distribution in Y, and we have a nice linear relationship. And these prediction errors, if you look at the dots around the regression line, they're pretty random across values of X. That can't be said of any of the other data sets in Anscombe's quartet. So if you look at the second one here, what you're seeing is not a linear relationship, but a quadratic relationship. So the values start out low, they go up, and then they start to dip down again at the higher end of X. That's a quadratic relationship between X and Y, not a linear one. We wouldn't be able to detect that without looking at this scatter plot. Look at the third one. You see this slight increase with one dot that's a little bit off the regression line and really contributes to negative prediction error, which makes up for all the positive prediction error in the other data points in that data frame. And then finally, this is one that's actually pretty common in psychology and actually in neuroscience. A lot of neuroscientists try to do correlational analyses with really small samples, and they're starting to learn that they can't do that. And this is a good example where you have all of your data points are right here. There's no relationship between X and Y if you just look here, right? So they all have the same X value and they have a range of Y values. Yet you've got this one extreme outlier way up here that's contributing to this correlation. It's driving it up to 0.82. So again, if you just ran a correlational analysis in R, just by running core, as you've learned in lab, for all 4 of these data sets, you would get the same exact correlation coefficient. So this just emphasizes how critical it is to just look at your data, know your data, eyeball it, and see and test these assumptions. Do you have linear relationships, and do you have homoskedasticity? Those are essential when interpreting correlation coefficients. Now, in case it was difficult to see these when I put all 4 of them together, now I'm just going to walk through each one of them individually very quickly. Again, this is a really pretty picture of a scatter plot, because what you see is you have across the range of X, you have some individuals who are below the regression line, then above, then below, then above, and below again. It's just sort of random across the distribution of X. That's what we want to see. That's a homoskedastic relationship between X and Y. So this satisfies the assumptions. Again, here, this is clearly not a linear relationship. It looks quadratic. And we just see that by eyeballing it. Again, this one, if we look at the prediction errors, we have one really big prediction error here that's driving these points to fall right along the regression line or a little above. So if we looked at the relationship between X and the prediction errors, we would see that there's something systematic. There's a relationship between those two. That's evidence of heteroskedasticity. It's a violation of the homoskedasticity assumption. And we wouldn't want to go ahead with a linear correlation analysis in this case. And then finally, this is the easiest one to spot. This is a no-brainer. You look at your data and you clearly have this one extreme outlier. If you notice, I actually had to extend the scale out to 20. The x-axis on all the others ended at 15. I had to extend it out to 20 just to get that guy on the scatter plot. And that's clearly driving this positive correlation. What's funny in real research is a lot of researchers, when they're looking for a strong correlation, they tend not to be bothered by points like that because it's helping their cause, right? They tend to get more bothered by points like this if we're looking for a positive correlation. Like people like me on the verbal and the mathematical ability relationship, right? It's very common to see researchers quickly spot those kinds of data points and discard them as outliers, but say, oh, well, no, this one supports my theory. Very bad to do, and as we get into multiple regression, we'll talk about actual procedures where you can assess whether something is a multivariate outlier or not, whether it's a multivariate outlier that helps your cause or hurts your cause. So to summarize this segment, there are a lot of assumptions going on when you're doing correlational analyses. So this is why I said I started with the famous line, correlation does not imply causation, because everyone knows that. But there's so much more to worry about or be concerned about when you're consuming correlational analyses or when you're conducting them. So here's just 3 simple assumptions that we talked about: normal distributions in x and y, linear relationship between x and y, and homoskedasticity. Then there are even bigger assumptions that we'll talk about in lecture 6. So reliability, validity, and sampling, which all fall under the umbrella of measurement issues, which is the topic of the next lecture.